So as a warm-up today, we're going to go over another one of the fundamental theorem of calculus, second fundamental theorem of calculus, free response. So if you look at this problem, it says the graph is a differentiable function f on the closed interval of -3 to 15. The graph of f has a horizontal tangent at x equals 6, and let g of x equal 5 plus the integral of 6 to x f of t dt for -3 less than equal x less than equal 15. So if you'll follow along on the paper that you've been given that you can see easier. So it says find g of 6. So filling in, since g of x is 5 plus 6 to 6 f of t d of t. Well, if you remember your definite integral rules, if it's 6 to 6, that's 0. So 5 plus 0 equals 5. Now, when we go to do g prime of 6, we're going to take the derivative of the g function, which is 5 plus 6 integral to x f of t dt. So if we break that up, we're going to take the derivative of 5, which is 0, and the derivative of 6 to x of f of t d of t by second fundamental theorem of calculus is just f of 6. So if we, or f of x, and then we'll fill in f of 6. So if we look at the graph on 6, the answer is 3. And then second derivative of 6, or g double prime of 6, equals 0, because it told you up in the instructions that you had a horizontal tangent at x equals 6. So that means the slope is what? 0. And when you take the second derivative of the graph, that would be the slope. Part B, it asks you on what interval is g decreasing, justify your answer. So g is decreasing where the first derivative is negative. So it wants to know on what intervals is g decreasing and justify your answer. So g would be decreasing where the first derivative is negative. So we know g prime x, first derivative, equal f of x by second fundamental theorem of calculus. So if you look up at the graph where it's negative, it's from -3 to 0 and 12 to 15. Now part C, it says on what intervals is the graph of g concave down, justify your answer. So g is concave down where the first derivative is decreasing because of the relationship between first and second derivative. So if the first derivative is decreasing, then the second derivative is negative, which means the original g of x would be concave down. So it's decreasing from 6 to 15. So part D is asking you to find a trapezoid approximation using 6 subinterval lengths of change of x being 3. So if you look up at your graph, if you have 6 subintervals, you're going to go 3, 6, 9, 12, 15. So if you look at the graph from -3 to 15, you can see that you're looking at the whole graph, and you're going to do Riemann sums. So n equals 6, and your width of each one is 3. So you want to do a trapezoid, so it's 1/2 height, which is your change of x, times base 1, base 2. So if I put 1/2 on the outside, we know change of x or t, our height, goes on the outside, which would be 3. And now we're going to look at each little interval. So an interval from -3 to 0 would be your bases. So you'd say f of -3 plus f of 0. and that would equal -1. Then your next little interval from 0 to 3, you're going to go f of 0, f of 3, which would be 1. Then your next interval is f of 3 to f of 6, which would be 1 plus 3. And then you're going to go f of 6 to f of 9, which would be 3 plus 1. Then you're going to go from f of 9 to f of 12, which would be 1 plus 0. And then you're going to go from f of 12 to f of 15, which would be 0 plus -1. So if you add all that up, you'll get 1/2 times 3 times 8, which will give you 12 units. So look back at each of these and see how I got that. If you go f of 3 is -1, f of 0 0, so -1 plus 0 is -1. So you're just looking at the outputs of these inputs. Now, don't get this confused with like the geometric. You're not making trapezoids by the shape. You're making a little rhyming sums between each of those intervals. And in the rhyming sums, you're doing trapezoid. So you would do base 1, base 2, which means it's going to be your left endpoint and your right endpoint. So don't get that confused with trying to find a trapezoid shape on the graph.